We've spent years of careful planning. We've sourced the most advanced equipment. We've brought together explorers, scientists, innovators to embark on a bold human adventure, redefining the boundaries of wheeled exploration. The first continuous circumnavigation of the globe by vehicle across both poles in 18 months. It was challenging. In just over 3 months, we crossed from Canada to Greenland, reaching the North Pole, the world's first surface continuous traverse by vehicle. Oh, not just adventure. Through exploration, we want to contribute to scientific knowledge. We took the first northernmost measurement of cosmic radiation coming from distant regions of our universe to the North Pole. The data we've collected will help our understanding of the universe. We also took the first continuous measurement of ice thickness to the North Pole and back. We know that science and new technologies have the power to improve lives and the impact we have on our surroundings. And we are not done. We will keep engaging individuals, organizations, and people along this extraordinary journey of extreme adventure, technological innovation, and scientific data collection, uncovering stories of human endeavor, tapping into the wisdom of ancient cultures, experiencing the world's natural wonders, inspiring today's innovators, technologists, and changemakers to boldly reach for the unknown.
Okay, so welcome to everyone. I'm very happy to host you here. This event is Global Car Expedition, Science at the North Pole, headed by Vasily Shakhnovsky. Is very important because it is not only a great and unique adventure, but it has a very high scientific value. So we are here in the building where Fermi and the collaborators, the famous group via Panisterna, with the chemist Oscar Agostino, Segre, Pontecorvo, Rasetti, Majorana, Iamaldi, made his research and discovery in many fields, in many topics of physics, quantum and statistical mechanics, nuclear physics, both with radioactivity and new forces like the weak force. So as you know, Fermi is considered a genius worldwide, and he was both a theorist and an experimenter. Here, just building, Fermi did his experiment on radioactivity by neutrons. And to arrive to the discovery of this radioactivity, a very important part was to slow down the neutrons. And this was done using the water of the fountain, the goldfish fountain that is just outside here. And around this fountain, there is also a plaque that was made by the Historical Physical Society, the PS, at the President of the Republic, Napoletano, when Luisa Cifarelli was president of this institute. So I just take the occasion to thank Luisa and all the other people present, in particular Paolo Nespoli, that is a famous Austrian. We are very honored about that. Okay, so the 22nd of October, 1934, in the afternoon, just using the water of this fountain, Fermi really realized the crucial role of the hydrogenate, with hydrogen, of course, material with hydrogen, to slow down neutron and to induce radioactivity. And this, of course, opened the way to really slow down neutron also in the case of fission. And this really was very crucial for the chain reaction in fission. So for his discovery in 1938, Fermi got the Nobel Prize. And after that, he left Italy and went to the States, first Columbia University and then Chicago. And he was back in Italy only for conferences to give lectures. And one of the last lectures was given in 1954, in a few months before he died, at the famous school, International Enrico Fermi School for Physics, that is in Varenna, Lake Como, and is run by the Italian Physical Society. So now, after this word, you understand why the researcher and the physicist here really feel in their blood the legacy, this important legacy of Fermi. And they obtain a really good result, not only because they're bright, but also because of this environment that is very inspiring. So I think, as you will see, here we will talk about our project, Extreme Energy Event, that is really fit with this, with your program. So we will refer. This Marco Garbini will do it. I will only anticipate that this project has a value both for science, but also for dissemination of culture. After saying that, I think I want to thank the organizer, in particular Paola Catapano, that did a great job to invite people here. And so then I wish you to enjoy the rest of this event. Thank you very much.
Can we use the mics now? Yeah, apparently works. So thank you very much for welcoming us to this prestigious headquarters, previously Enrico Fermi's location, where so much important physics and historical physics has happened. And thank you for welcoming the Transglobal Car expedition here. As you said, it's not just an exploration feat. What they did also something that is very valuable for science. They measured cosmic radiation at the North Pole for the first time ever, beating a previous record that my expedition, the Polar Quest, did together with Luisa at the 82nd parallel. You went up to the 90th parallel. We'll talk about that, and with Marco, we'll explore and understand why it is important to measure cosmic radiation at the North. But let's start from a video contribution from somebody who is not here today, but recorded this message. This is Kim Holman, the special advisor for Norwegian Polar Institute. And his talk is about the ice is melting, we all know that, ethics of the Arctic.
Thank you for this opportunity to reflect a few words about our book, The Ice is Melting, Ethics in the Arctic. I have been working for well over 35 years with climate change. Polar regions are sensitive, and the Arctic in particular is affected by climate change, altering nature and human lives. It is often said, almost a cliche, that what happens in the Arctic does not stay in the Arctic. And most of the changes in the Arctic are imposed from emissions and human actions outside the Arctic. We need more data and innovative ways of acquiring knowledge. But the world is rapidly losing habitats, ecosystems, and biodiversity. The book emerged from my opinion that despite that some may argue that we have incomplete knowledge, we must discuss the values and actions that we can take now. Environment knows no borders. Humanity must find ways of coexisting with each other and with nature with a long-term, maybe even infinite perspective on salvaging a planet that supports life. We are 8 billion people on the planet. All need food, health, and safe housing. This will, of course, leave a footprint. But we need to look at how to live our lives with a healthier footprint. As we impose increased change on the planet, the future becomes increasingly uncertain. How can we prepare for the uncertain? Well, we must have as many options available as possible. Options means diversity. Diversity is more important than ever for our own future. Human diversity, biodiversity, and natural diversity are essential. We must protect them all. But diversity is not enough. We need a healthier footprint on our planet. I observe that friendship, love, family, art, culture, nature, diversity, and peace are priceless, but all have small environmental footprints in themselves. And they all provide for a better emotional life. I believe there is a pathway forward where we develop society using the emotional well-being of human beings as guiding principle. A world order where growth and development is measured in quality rather than quantity, where emotions are more important than money transactions, where humans are more important than things. We can work together for healthy futures for the polar regions and our planet, where friendship, love, diversity, nature, and peace flourish with dignified lives for all. The ice is melting. Ethics in the Arctic was written as our first stepping stone to move in a direction that provides a better future. I wish you great success with your meeting, and thank you all for listening.
Let me take one word that Kim Holman said, the ice is melting. You saw it with your own eyes, and during the expedition, you had to find solution and adapting to the ice that is melting. That is a very nice metaphor of what we all have to do, adapting to the ice. And I think this ties in very well with what you are presenting here. Andrew Comrie-Picard has participated to the conquest of North Pole with the expedition. You went all the way from New York City through the Canadian Arctic to the geographic North Pole, then back to Europe. And you are joining the expedition again on the route to the South Pole. So you are the perfect testimonial to, on behalf of the expedition, tell us about it and what you saw up there.
Of course. Well, first off, thanks so much for having us here today. It's a real honor for the TRANSGLOBAL CAR expedition to be here at the Research Center of Enrico Fermi. I mean, what a wonderful welcome we've had both in Rome and in Italy, and the partners that have been associated with us here. And it's been a really great opportunity for us to spend some time doing some learning ourselves, and hopefully augment that with eventually doing some teaching with what we learned. So I'm going to walk you through what happened a little bit on our North Pole expedition, some of the numbers associated with the distances and the time that we've traveled, some of the challenges that we've had, and talk a little bit about the future of where the expedition is going next. My name is Andrew Comrie-Picard. I'm a main team member on the TRANSGLOBAL CAR expedition. As Paolo Nespoli explained to me on the space station, nobody gets to do only one thing when you're on one of these kind of expeditions. So you have to be able to do everything. He described fixing the toilet. We had to fix the cars, do everything. But one of my main tasks also is being sort of the science liaison officer for the expedition. So in terms of making sure the equipment's calibrated, making sure the data is getting back to the various partners. I am privileged to be able to do that. It's one, as many of you know who work in science, it's difficult to collect data no matter what the circumstances to collect them accurately. It's very difficult when it's minus 40 degrees with a 40-kilometer-an-hour wind. I know that Paolo knows this, but it has to be done in order for the data to be accurate. And that's exciting for me to not only have the challenge of doing these expeditions, but to be able to collect the data. You have a couple of other people in the audience who have done the entire expedition. Vasily Shagnovsky, the expedition leader, is here, of course. Max Badlin there, our videographer, cinematographer, went over the North Pole with us, is continuing with us the whole way. And we have a number of extended team members here also. I won't introduce all of them, but family members and extended team members who have done so much in order to make the expedition work at all. It takes a village, as they say, and certainly we have a big village that's run this thing. Let's go over the slides a little bit about what I'll show you about what we've done. Is the we can go past, that's you.
Yeah.
We'll go past that slide. We have achieved what is the first wheeled expedition over the North Pole on the surface from North America to Europe or in that direction. It has actually been done once or twice before, you could say, by our own team, by members of our own team. I was doing an interview with CBC in Canada, the National News Network, and as I was doing it, I turned around and looked at the people behind me and said, you know, we have some of the world's, we have half of the, all of the world's experts at driving on the poles are in this expedition. Everybody who knows how to drive a vehicle or anything with wheels on the poles is in the Transglobal Car expedition. And it means that, you know, it's thanks to Vasily Shagnovsky's organization that we're girded for success. Thanks for having all that team together. And that's just in the core team. So let me talk a little bit about some of the things we'll see here. You've got an image on the left there, a kind of a rough map of the direction that we took to go across the North Pole. We left from New York City, and I'll get to some numbers in a second. That's the bottom right. You see some of our vehicles in Times Square. We left from the Explorers Club on January 9th, 2024. On the upper east side, and then went through Times Square, and then left the city and traversed across to Yellowknife, and then from Yellowknife over the North Pole down to Greenland. I'll show you that. But there's some images from the beginning of Times Square, and then that photograph in front of the vehicles is just before we made landfall in Greenland. Let's go to the next slide. So in terms of numbers, and yeah, there we go. In terms of numbers, we're thinking of the whole Transglobal Car expedition, which is around the world from New York City through both geographic poles, through the geographic North Pole. Now, as you know, we're here through Europe, through Africa, then across Antarctica in a new way that's not been done before, up South and Central America, back to New York City. We consider the Arctic leg that we've achieved to be sort of the first leg, or this first and second leg. The first leg was really to get overland from New York City to Yellowknife, which is the jumping off point to go over the tundra and the ice to the North Pole. So that was about 5,000 kilometers. In total, that whole Arctic leg, say 10,000 kilometers, took us about 4 months to go from New York to Yellowknife to Cambridge Bay to Resolute, which is sort of the last indigenous community, last place you'll see people, and then across the pole to Greenland. 5,000 kilometers, the first month of that was to get from New York City to Yellowknife. And then from Yellowknife, we took a reset, changed vehicles to large tired 6x6 Arctic trucks that are very experienced in crossing Antarctica with Icelandic people who are very good at crossing glaciers because they have a glacier that they can drive on all year. And they're also in the team. These are some of the experts I'm talking about. Then we went 4,500 kilometers from Yellowknife to a place called, 45 kilometers. Let's say we went about 2,000 kilometers, 1,800 kilometers to get to the last island in the archipelago of the island diaspora of Canada. That was over first the tundra, about 800 kilometers of tundra, which is very difficult work. And when we first innovated the route 2 years ago, it was the first that any wheeled vehicle had done it. Of course, indigenous people have been crossing this area for thousands of years, and occasionally you get a snowmobile that tries to make the trip as an achievement. But we're certainly the first vehicles to have gone across. Then from Cambridge Bay, which is sort of our reset place in an indigenous community that's been very, very helpful. You know, we're talking about how we make partnerships, and Paolo has helped us find so many people, and Paolo and Fabrizio. We've made so many friendships in the European scientific community. We've also developed such great relationships with the indigenous people, the Inuit in the north of Canada, with our 4 visits there now, and deep visits where we've had to supply and work. And in fact, I now have an indigenous name, Omilgokdok. I'm the men with thin lips. Which is actually a great honor for me as a Canadian, and it's been part of the wonderful thing has been learning the fabric of the indigenous peoples in the north that's allowed us to really be able to do the expedition at all with their assistance and their guides. Can I get the slide back up? Thanks. So then from Isaacson, which is if you've ever seen one of those haunted so-called weather stations, but really radio listening stations that were built across the north of North America and Europe in the Cold War. It's an abandoned station, which has haunting images. Very interesting place. It was the last place we saw any civilization. From there, it was about 1,400 kilometers to the North Pole. It took about a month. Now, the vehicles that we used for that, you can see in the center photograph there, are amphibious vehicles developed in Russia. They're called Yamelia. They are built by a very innovative Russian explorer named Vasily Yelagin, who is also on our team. He's the one who's previously gone to the North Pole from the other side with them. They have 51-inch tall tires. They're able to float, so they're amphibious. And what's crucial is that because they have an alternator with an engine, it's a very small engine. They're actually very fuel efficient, a very 2-liter diesel engine out of a Toyota pickup truck. And even, despite being very, very large, they're very, very light. They weigh about the same as your average passenger car on the street here because they have to be able to float. They're made of very thin aluminum, very aeronautical engineering ideas. Everything is very, very purpose-built for this one thing. So they're able to cross this ice. The tires assist with the flotation. There's a double hull in the vehicle, so it's able to float. We don't have a propeller or anything on them. They're not boats, but we're able to cross open ice floes, which, as you mentioned, Paolo, is crucial because we've seen changes in the ice, which I'll get to in a second. Anyway, it took us about a month to go to the North Pole over that 1,400 kilometers. It's terrifically hard work, and you have to be very, very innovative. We have cracks in the ice that you come across. You saw in some of the video there, very large ice hummocks, we call them, or pressure ridges where the ice is pushed up against itself and created these large towers of ice. And you have to get out and physically chip them down with ice picks as a group, and then find a way to crawl over them with these 6-wheel drive vehicles. It's I have spent a lifetime of doing very difficult things with vehicles, and it's amongst the most difficult things I've ever done. And everybody who's ever done it is in our expedition. So it's very, very specialized. We got to the North Pole on April 6th. Which was a terrific event. Of course, we celebrated it greatly. We had excuse me, you saw some of the video there. We had a couple of airdrops of fuel and food in order to get us there, and needed that. And then on the North Pole, actually, I was just speaking with Fabrizio Bernardini about this. We were able to use GPS data, and I want to get to some of our partners in a second. We were able to use GPS data to see that we were actually on the geographic North Pole. Before 1996, it was probably that anybody who'd gone to the geographic North Pole was kind of approximately at the North Pole, but we had the actual GPS data to know that we were standing there at that moment, and then that we weren't standing there at that moment because, of course, the ice on the top of the world is constantly moving. So we identified, we did our photo opportunity, we did our video, and then we watched our GPS as pulling us away from the North Pole and started almost running across the ice to stay on the North Pole because it's a challenge when the ice is moving all the time. Then from there on April 6th, we began the southward journey back down to Greenland. That 800 kilometers to Greenland was by far the most difficult of the expedition. We always knew that it would be difficult because the way that the Arctic ice flows and the ocean flows pushes the old ice, the pack ice, down towards Greenland, and then it refreezes in large columns, some very old ice. And the polar ice cap, which rotates countercyclically to the Earth, it grinds up against ice that's frozen, land fast ice that's frozen to Greenland. And it creates both a very choppy, very difficult interface there, but more importantly, it can drift far apart and then drift back together. And when it drifts back together, it can be in terrible shape. We knew it would be difficult. And indeed, it was at least as difficult as we anticipated. So we got down to that. Not only was it very broken up, the pack ice was very tough. But there were very large gaps. We spent a lot of time using drones as a new technology, but also, thankfully, and this is really what I want to lean into later when we talk about partners, Aegeos, if that's how I correctly pronounce it, Fabrizio Bernardini, through the relationship with the space agency and the satellite imagery supplier, was able to get us very, very accurate satellite imagery, which greatly enhanced our ability to be able to navigate over the ice because the ice changes every day. And so we were trying to get fresh shots of the ice every day in order to be able to navigate at all. And it was a terrific challenge, which I'm going to get to in another minute. But anyway, that 800 kilometers took fully a month. I need those slides again for my aid memoir here. It took us fully a month, and it was very, very difficult. So in sum, then, 3,700 kilometers on ocean ice. That's either driving on top of it or chipping our way through it. We did a little bit less than 1 kilometer, let's say, in the water. And this is in 5 or 6 water crossings where we had no choice but to put the vehicle in the water. And as I say, I've done a lot of things with vehicles, but until you've taken a large amphibious vehicle and driven it off the end of the ice shelf into the black frozen Arctic Ocean at about 10,000 feet of depth, 4,000 meters, I mean, in my world, you haven't lived until you've done that. But I don't recommend it for everybody. It's a very big moment when you splash down and get the water over the windscreen, and then it bobs back up. Thankfully, most of the time, all of the time. But it definitely is in terms of excellence, technical excellence. It's a very big challenge. And then I'm saying there's about 10 kilometers. I don't have a hard number on this, but the 10 kilometers where we were driving on ice that was as close to water as you can possibly be. You can see some of our videos. We're driving across a sheet of ice and it's flexing. There's actually, you can see the wave underneath us moving as we move forward. Now, of course, saltwater ice is more pliable. It's not as hard as freshwater ice. And so we're able to work with that flexibility quite often. But again, until you've been driving across a sheet of ice and looked in your rear view mirror and see the whole plate moving behind you, you haven't lived, I say. So if you think about that when you're driving through Rome later today, that it could be worse or it could be different anyway. So let's go to the next slide and talk about some of the challenges. So notable. We're not doing this for records. We're not doing it except because of the great challenge and for the science that we hope to be able to support. But it is the first wheeled expedition from North America to the North Pole. Never been done before, and we've achieved that. It's the first pole-to-pole circumnavigation of the Earth on wheels. That's not complete yet. We're in the middle of it still in Europe, going down through Africa, and then we'll cross Antarctica, South America, Central America. But we anticipate that will be the world's first. We will finish, we hope, in May 2025. The G there is it's probably a Guinness World Record. We're speaking with them. It's the first continuous ground survey of ice thickness. And this is a wonderful thing. Well, this is getting into science. So we'll have an address later from Christian Haas. We have worked over the previous years with him with an electromagnetic resonant device in order to measure ice thickness continuously behind the vehicle. So previously, if you wanted to measure, well, the easiest way to measure ice is to go up there and drill a hole in it and measure how thick it is. It's kind of what you have to do a lot of the time. Satellite imagery is very good at measuring ice cover, extent of ice, open water. It's very difficult to measure thickness of ice. And so what we were able to do is carry this electromagnetic resonant device behind us the entire trip and log data the entire way, which has never been done before. If somebody's skiing to the North Pole, well, they can carry it behind them for a while, but it has to be powered and it's quite large. What Christian Haas has previously done is fly a twin otter in on skis, go to various points. You have to be able to land it. You have to be able to safely take off again. So you can only land in so many points. But we were able to continuously survey this across the pole. And Christian, I hope, will speak about it. That's a great achievement, we think. We hope. Then it's the highest, as Paolo said, the highest latitude measurement of cosmic radiation at sea level. First,
the highest possible.
There's no. Well, I was going to say, Paolo, when she said it is the highest, surpassing a previous record that Paolo held, I wanted to say that's okay, you'll get it back, but you can't because we've done all the way. We've got 90 degrees north, but I'm sure you will set other records in your travels. But we have now not only surveyed the cosmic radiation penetration at the North Pole, but continuously from New York to the North Pole down to Greenland and beyond, and are continuing to survey it even now. So that's something that we hope will add a contribution. We also had some interesting cosmic storms or solar flares and storms during that time.
Especially on the 10th of May.
On the 10th of May, yeah. So we were able to log data during that time. And then there's something else. The first, yes, well, of course, this is with our partners from Igios. The first satellite pictures of cars in the geographic North Pole. Of course, I mentioned that the satellite data that we were able to get was so crucial for our navigation. Well, it also allowed us to get an image of our vehicles at the North Pole. So there's evidence, but it's just a fantastic, in our minds, a fantastic image to be able to see ourselves in a satellite image with what we've achieved. So thank you for that. I look forward to speaking more about that. A very big image. I think they're going to speak to it later. Let's go to the next slide.
Google Street View couldn't do that.
Yeah, that's right. We could have had the Street View. So people ask, and this is just more a bit of fun, what was it like to being on the expedition? I have a friend who flies transoceanic freight aircraft, large freight aircraft, and he always describes it as hours of boredom punctuated by moments of terror. Because you're looking out for days and days, weeks, literally, at a vast white desert, and we're getting out and chipping it, and getting in, back in, and driving, getting out and chipping it, and then things happen. You'll have to look at our videos online, but the ice sometimes is moving against itself, and we're having to hop from one ice floe to another, or we have a set of aluminum ladders that we throw down and very quickly drive across. I've driven across plates of ice that are shifting. And as I drive across them, they move over. And then the next vehicle behind me can't cross the same place that I just crossed. And so we have to find another place to go around. It's actually, there are some very exciting moments. And like anything, though, maybe this is the way it is with, I don't know, bullfighting or anything. By the time you've been doing it for 4 months, it becomes almost banal. You're like, oh, we're going to have to cross another bit of open water. I'll just drive the vehicle in the water again. Or oh, the ice is all moving. Well, let's see. We'll put a couple of ladders there. You go first, go fast, and then we'll go next. It's like any team that works well together. You develop techniques, and what was previously terrifying and novel and exciting becomes just what you do every day, and that's what it did become like. So like that, and then what's next up here? Give me another fly-in. Oh yeah, 2 full months alone, and we were the only human contact to the North Pole. Now, if you go on an expedition, almost any expedition in the world, you can, if you go climb Mount Everest and so on, you expect to be some number of weeks with just the same number of people. But because we were in an area of the world where there is no one else, we were only with ourselves for 2 months. So that is, of course, a social challenge. And this is actually, we took advice from Paolo Nespoli about being on the space station and about being a good person, because it's important to get along with your teammates. But it was a test, and it was a test for me because language-wise, I was in the language minority, and it was a great test for me, and that's something that we hope to write and speak more about. So 2 full months with the same people it's a little like going into a battle, and we felt that, and we share a lot of common language now. What's next? Right, and this is interesting, and this was unexpected for us. We went more than 2 months with no sign of life at all. Of course, the indigenous peoples have taught us, and we've seen that it's possible to track animals across the North Pole pretty well. You see bear prints, you see bears, which is fantastic. But you see bear prints, fox prints, rabbits, some evidence of birds. But that evidence ran out by the time we crossed the 85th latitude. And we didn't see any signs of life, hauntingly, until we got to the North Pole and headed back south. And then we saw a small blue tarn, the first bird we saw, which seemed to me like when you're in a desert or when you're in a white desert, it was like a splash of blue in this small bird. It was a real eye opener. But it's something we didn't expect. Big thoughts. Well, so you spend 2 months in a white desert with people, you start to have some big thoughts. You don't talk all the time. And certainly it gave us lots of time to think about the changing planet and the climate, and looking at so many miles, so many square kilometers of ice, and also feeling, I didn't mention this in the list, feeling the reflective function of the solar radiation that ice offers, because we had almost 2 months of polar day. That's the other thing I didn't mention. It was one of the reasons we had to delay until the date that we basically got up onto the ice was that it was too dark to navigate over the ice, but then very quickly, because of the latitude you're at, it shifts from polar night to polar day. And so we went 2 months without the sun going down. That affects your circadian rhythms. We spoke about that ahead of time with Paolo, and how that can affect you personally and can affect your interactions with other people. But also, you're looking out of that ice constantly for 2 months, realizing that it's reflecting the sun's radiation, that the change in the ice is going to have and is having a change in the temperature and the cosmic the UV and other penetration of the surface of the planet and warming. That's very impactful. You can hear about it, you can talk about it, but when you see it for a long time, it had a big impact on me. Let's check the next slide here. And I'll wind up quickly here. A few bits of advice. If you want to do a transoceanic or transglobal, if you want to cross the North Pole in a vehicle, I'm going to give you a few recommendations just for your next trip. The first, I'm going to say, take yellow lenses with you. It turns out if you're looking at the white surface for a long time, it can burn your eyes a lot. We all had very good glasses. But because the light can be very white, as you can see that top photo there, our vehicles are very bright, relatively speaking, bright red, and that's on purpose. But you can't see the horizon there. You can't see any ice hillocks. You can't see really anything at all. And that makes it very difficult. You strain your eyes, and you're driving for an hour. You're driving all day long, and you're trying to pick out any features on the surface. It's extremely difficult. Yellow lenses help a little bit. I mean, enough that you have to have them. What's next? What's my next advice for you to take if you're going? Oh, yeah, you have to like fish. And dried food. Our food source, we took 140 kilograms of white fish that we purchased in Yellowknife from the fishermen there. And it was easy to put them in the refrigerator because we just wrapped them in saran wrap and hucked them in barrels behind the vehicles, and they froze. And then you can just shave them off and eat them. I learned these techniques on this expedition. Just dip them in salt and pepper or in soy sauce and eat them like sushi. Or you can broil them, or you can fry them. And we've eaten that kind of fish, I think, in every conceivable way. You know, eventually you start to like it. Also we various varieties of dried food from American sources, Norwegian sources, Russian sources, and I've actually learned a lot about Russian food thanks to the dried Russian food that we had in the expedition. You have to like that too. I recommend that you have, or at least you start with good knees. It's a little hard to see there, but you see the hard weather. That difficult weather on the bottom right there was coming south. Some of the most blustery weather we got coming south from the North Pole. But you can see there, it may be difficult, but the door aperture there is more than a meter off the ground. So every time you get in and out of the vehicle, which is about 1,000 times a day, you jump down about more than a meter. And onto uncertain surface. There could be slippery ice underneath. It could be a deep snow. It could be shallow snow. So you're getting in and out all the time. It's very athletic. It's a bit like being a climber. You climb up the tire, but it is fairly hard work. What's the next? Oh yeah. And so then another one there that's fun is you can see we have an aluminum ladder. We use the drones extensively in order to look out over the ice, but in fact, there's no substitute for your own eyes. And Vasily Login, who innovated all of the devices for this vehicle, innovated that ladder, which goes up from one of the vehicles, and a thin Dynex line, climbing line, holds that ladder up, and you scamper up it to look out over the surface. And you just rely that the guy on that line, it's tied to the vehicle, doesn't give it a little wiggle, and he usually does, just to bug you. But that's how we look out over the ice. Let's bring that up again if we can, Alexei. This is if you're going to sleep in a box, and we slept inside indeed because of one of the reasons when we use the Arctic Trucks vehicles, we sometimes sleep in tents, and we have in Antarctica, and we will. But you don't want to do that in the Arctic, thanks to polar bears, which for which it just makes a yummy soft center to their meal if you're sleeping inside a tent. So we sleep inside these Yamelias. They're like campers. If you're going to do that, and it's going to be minus 40 degrees and 30-mile-an-hour wind, just don't drink a lot of water before you go to bed. It's a difficult thing. And now this is the most important thing, and this is to have a good team. And on these expeditions, you do, in a sense, get to choose your team members, and Vasily Shagnovsky did. But you need to have the competence, obviously, the technical competence in order to do this sort of expedition. But they need to be people that you're going to live with for months and work with in every possible way. And that goes for the extended team too, some of which we have in the group here. You need to make sure that you have personalities that are able to work together, and that's crucial. That's in terms of the actual team members. But you also then expand it out into partners and people that you work with. And that's been crucially important to us. And so Paolo Catapano and Polar Quest, I'd like to thank you so greatly. Rosie Mondardini, like fantastic work that you've done, not only yourselves, but for the other people you've connected us to, like Paolo Nespoli. And also crucially, of course, Fabrizio Bernardini, who has helped us out so greatly, hooking us up not only with his relationships with the Italian Space Agency, but with Aegeos for the satellite imagery. And thank you so much for that. You literally cannot do it without partners like this. And that's why we're excited. We spent this morning at the Italian Geographical Society, and we're so happy to be here at the Enrico Fermi Institute, because it's relationships like this that are crucial in the end. We're pretty good at going across difficult places, and we'll go across Antarctica, and we'll go do some work in Africa. But it's only possible to make that important and make that land if we're able to have relationships like we have with all of you. So thanks for having us, and thanks for letting me talk a little bit about what the expedition's like. Any questions at the end? I'm happy to talk about it.
Thank you, Andrew. Thanks, Andrew, for very kind words. We do have questions. We are being followed by a bunch of kids, actually, from various places. There's children from Uganda following us from Lebanon, but also from Italy, from an association called Spazio alla Conoscenza. And there's one young girl who wants to ask you a question that she sent me on my mobile phone. So this is Mia Rocca from the Istituto Tecnico Ciampini Boccardo, Novi Ligure, which is in the northwest of Italy. And she asks you, what was, among all these challenges that you described, the toughest from the logistics viewpoint during the crossing of the ice?
It's hard to there are challenges in an expedition like this at every possible level. I would say that normally you would say that the huge logistical challenges are the big challenges, because we had to move vehicles across the earth. I mean, Zurab Sendikizi is here, like, you know, just the border, the paperwork, the getting things in and out, the containers, the wheels, and oh God, the logistics are incredible. And then the fuel drops. I had the privilege or the challenge of organizing the manufacture of fuel bladders in Australia, and then connecting them with the parachutes and putting them in airplanes in Ontario and flying them up. I was on satellite through my mobile phone, talking to the airplane on their satellite phone to triangulate, and then the first thing we'd seen for months flew over us and hucked stuff out at us. Like, just the logistics of doing that is massive. But to answer that question, I think I'd have to say it's at a personal level. You have to dig really deep a lot of the time in order to get out of the vehicle again and go out and chip ice again in a whiteout, in a blizzard, in such difficult circumstances, and never not think of doing it. And you know, that's true of any athlete or anybody on any of these expeditions. You've been on them yourself. It's just that sort of unquestioning devotion to the outcome, and it unites everybody on the expedition. And Vasily Shagnovsky has done a wonderful job in choosing the people on the expedition, the people back at home who've been supporting us. But it's just the biggest challenge is never give up and never say die. And on the other hand, it's almost the easiest thing, because you just never question. You just do it.
I fully agree. And what I used to say is that after these expeditions, of course, if you survive them, you are an augmented person. It's an augmented version of yourself. And it's very true. It's as if you discovered another layer in yourself. So thank you. It was a bit longer than foreseen, but it was worth it. Thank you very much, Andrew. So we now have on my left, Marco Garbini from Centro Fermi. He's a physicist. You can go there. Yes, okay. No problem. So Marco is a physicist from Centro Fermi, and he directs or he participates, a big contributor to this extreme energy event project, which studies cosmic ray on a citizen science level. It's a serious scientific study, but it involves a lot of school children at the same time doing science with you. So
thank you. Thank you very much for these very kind words. And thank you and welcome to you here at Centro Fermi as a Centro Fermi researchers. Me and my colleagues are really happy you are here, and I hope you enjoy the staying with us. So let's start. Why we measure cosmic ray at north latitude? I can't say highest north latitude since it's up to you. And so please, first of all, a few words about the next one. Thanks on cosmic rays. I think everybody, or I hope you know that we are all the days bombarded by cosmic rays arriving to the Earth atmosphere. They interact with the atmosphere, and then some particles, showers till ground, arrives to us. They have galactic and extragalactic origin, so they come from far, very far from us, and they have a lot of information that we know since the beginning of last century. So we know the composition of cosmic rays. We have largely studied the energy spectrum. So we know that the energy spectrum of these cosmic rays is very wide. So a lot of energies from lowest to highest energy. And then now we have started since some time the study of cosmic rays connected to the climate, to the weather, to the environment that we live in. Okay, so this is just the beginning of this work. And sorry, next one. One curiosity, maybe you don't know that one of the main and one of the many contributions that Fermi made during his life to the physics was also connected to the energy spectrum of the cosmic rays. It's just, he proposed a model for the acceleration, the energy, and that was, of course, correct, I would say. So this is just a curiosity. Then next one, thanks. Okay, thank you. If we believe that the beginning of the cosmic ray studies that they were neutral particles, now we know that they are most charged particles, and we discovered it knowing that the Earth is surrounded by its magnetic field. So the magnetic fields of the Earth prevent all the particles to arrive. Some studies from the beginning of the last century again demonstrated that these were positive charged particles. So now we know that basically almost all the cosmic rays arriving at the highest part of the atmosphere are protons, at I think 90% is the right percentage. And we can imagine that our atmosphere and our magnetic field of the Earth is the medium that prevent all the radiation to arrive to us. So the Earth atmosphere and the magnetic field give us a protection from cosmic radiation. This is something that is important indeed for astronauts or pilots or aircraft. So studying the behavior of cosmic rays is some way related to our environment, to our world. Next one, please. Few words about one experiment. The experiment that I lead, that was proposed in 2004 by Antonino Zichichi, and is a collaboration between Centro Fermi and INFN, is an experiment that is devoted to the study of cosmic rays at ground. So here is also an important scientific education role, because we make the experiment together with the schools. When I say together, I mean together. As you can see on the map, the red bullets are detectors that are inside schools. Okay, so we build the detectors together with the students and bring them inside the school. Now we have something like 60 telescopes for cosmic radiation, and we are studying the behavior of the flux of muons along Italy, and we have also some detectors at CERN. So this is the most important part of the experiment, the fact that we study cosmic rays, and we did also scientific dissemination in the schools. Inside this main, please, next one. Inside this this experiment, we, as you can see from the slide, students go at CERN to build the detectors. Then they install the telescope at school, they monitor the detector along their running time, and then participate in the data analysis. Today, this is the largest AMR-PC-based cosmic ray observatory, where AMR-PC is the acronym of our detectors, multi-gap resistive plate chambers. Next one, please. Oh, then in 2018, we joined the Polar Quest expedition, building a dedicated cosmic ray detector that should be some way different from the one we put in the schools. This was a very light detector, 50 kilograms instead of hundreds. And it was also low power consuming, 15, I think, watts, because we had to put it inside the Nanook boat that was going around Svalbard, reaching 82 and something, and taking data from the very first day till the very last day of this mission. And we also built other 2 detectors in the meantime, because we continue proposing this to the school. So one was on the boat for this scientific adventure of the Nanook. Then one was in a school in Italy, another one in a school in Norway. And next one, thanks. So this is the data, the main facts about this mission. The one that is more related to my job is the 1 million muon tracks that we acquired basically without stops in the data taking. There was one, I will leave you it at the end, because it was really a nice event that helped us at the end of the story. So you can see the path of the boat. The yellow is not is the path using I think Google or something like that, and putting the yellow point if there were data. And if you can see, if you see, there are data all along the journey of the boat. So next one, please. Next one, please. Okay, so we can measure the flux of the cosmic rays as function of the latitude, and the behavior is exactly what we expect due to the geomagnetic field of the Earth. We expect that the geomagnetic field is lower at the poles, so we see much more cosmic rays, because this field doesn't block cosmic rays, so they arrive, and is increasing at lower latitudes. So this is something that is some way expected, but you have to measure. First of all, this is the first point of our job. And okay, there are some gaps. I will talk about them. And anyway, this becomes a way you can monitor the magnetic field, for example, of the Earth. Let's go to the next one. Then, since we started, thanks to the Polar Quest 2018 mission, we started a collaboration with the CNR, so the Consiglio Nazionale di Ricerca in Italy. We had the possibility to install the 3 detectors that were used in 2018 directly at Ny-Ålesund to the Svalbard, where there is an international research center. So we have, till that date, 3 detectors taking data there at the highest latitude. Why we want to do that? Because we can monitor day by day the behavior of the cosmic rays. So how many cosmic rays arrive at ground? And so we can correlate this behavior with many other parameters, because that is a big research center where the climate, the environment is completely studied by all the quantities you can imagine. I just say temperature, for example, pressure, atmospheric pressure, pollution, everything is monitored in that research center, so we can correlate our data with the data coming from other institutions. And moreover, the pole, the region near the pole are more sensitive to what happened to the Earth. So if you stay there to make measurement, you can realize that something is happening before, okay? If we see the temperature increase of 1 degree here at North Pole, you see more and you see it before. This is the main reason why it's useful to go there to make measurements. Next one. So then we fill a bit that plot using data on the ship Amerigo Vespucci in 2022. And we would like next time to fill the gap between 50 and 70 degree in latitude, making other measurements, maybe using a car. Actually, you have a really amazing car. I see the one parked there. That is more than enough. We can maybe discuss about that. And this is a really nice plot that is inside. There's a lot of work of many people working on this. It's not so trivial. There are a lot of correlation for each point, and I will talk about one point later on. And next one. Okay, this is, for example, what happened when you have detectors always turned on. Okay, you can see solar flares, and you can see that when something is happening on the sun, something will happen also here where we are. And this is the last, the last solar flares, but we measured a lot. And the bottom plot indicates the fluctuation of muon rate. Muon are the particles that we measure at ground during the time. And you see that you have maximum and minimum, and this behavior is with annual periodicity. This is expected. It's connected to the atmosphere, the temperature, the density. These are particles that interact with matter. The matter is more or less densely connected to the temperature, so you get maximum and minimum. But you see also that there is a general trend to lower down that is connected to the sun. So the sun is going towards its maximum in the solar cycle. That means that there's a lot of influence on us. More work from the sun, less the particle that we see. So this is, again, something that we expect, but we can study, we can monitor, and we have an handle to see what happened on Earth using cosmic rays. Next one. Okay, going back to the to the question, why? Well, it's amazing. You can't say that. It's amazing from the scientific point of view, but it's also amazing from the pictures, easily. So from my point of view, I would like to wish you good luck for your expedition. We look forward for your data from the South Pole. Maybe we can just compare the data. And please, next one. Next one. Okay, just my suggestion. I'm not so in contact with adventure, but any event, also unexpected, can be an opportunity. Okay, something happened on 30 July 2018. The Nanook get stuck due to the low tide, so they went down till 45 degrees, I think. So it was not 42. It was not comfortable. But next slide. Since we are just physicists, please next. Okay. We simply use that data to check if our orientation correction for the cosmic rays was working well, because if you look up to you, you see 100 cosmic rays. This is a number just given as order of magnitude. If you go that direction, you see 50. So they are lowering. So when you go down with your boat, we see our detector was on the top. We see less cosmic rays, and then we just used some correction to get the final result, that is the red curve. So it was useful for us.
It was useful. We didn't tell anyone. And when we arrived at the port in Longyearbyen, everybody knew. And I said, how do they know? Do they have satellite spies on us? No. You, Centro Fermi, put the data on Facebook.
Maybe.
And the portmaster, Longyearbyen, said, Nanook, you got stuck. Did you break anything? Yes, we didn't want to tell them because we were afraid they wouldn't allow us to go any further, but we could repair the broken piece. It was a broken central board of the boat. And then,
okay.
So
okay. This is the end. Thank you very much. Again, welcome.
When you work with
good luck.
Thank you, Marco. Don't go away.
No?
Don't go away, Marco, because one of the students of the Spazio alla Conoscenza project, Grazia Cornelli, Istituto Tecnico Ciampini Boccardo, Novi Ligure, she has a question for you. Among all the results that you explained, what is the most important one? Measuring cosmic ray at north latitude, what's the most important result that you expect to find?
In my opinion, we have not yet reached the most important result, but we have started the path towards the monitoring of our planet using a new tool, the cosmic rays at North Pole. And well, actually, I really appreciated in our result the fact that we see the solar sun cycle. This was very interesting to me. And I think that the most has to come. This is but it's important to keep it on and ongoing. That's the point. Thank you.
Thank you very much, Marco. And so this is now the right time to go to CERN, where James Devine, the scientific advisor to the TRANSGLOBAL CAR expedition regarding cosmic radiation, can connect, because he built the detectors that you brought with you to the North Pole, and he's building right now one detector that is ready to go with you to the rest of the voyage. Do we have James on the Zoom?
The northmost measurement of cosmic radiation made at the North Pole. I'm going to give you a brief introduction to our detector, how our detector works, what the pieces are, how the measurement was taken, and what we found so far. This is one of the types of detector that was carried on the expedition. And inside here is a cosmic pie. Normally we put these in non-waterproof boxes, and we shipped quite a few to schools. But in this case, we had to make some modifications to our design so that it would stand up to the rigors of the North Pole. And inside, I can open it. So this weighs about 1 kilo. For those people in the audience, we've got some circuit boards, and underneath here, we have some scintillators. So these are actually the detector elements. There we go. And it looks a bit like a wrapped chocolate bar. There are actually 2 scintillators inside here. So these are a much smaller version of what was carried on the Polar Quest expedition. Scale down so that you can fit it in a briefcase. This weighs 1 kilo as opposed to 50. Do we have the slides yet? Perfect, that's great. So if we could maybe skip on to the 3rd slide. So 2 slides forward. There we go. So here you can, back one, there we go. You can see on the left-hand side a simulation of what happens when a muon, so these are the residuals of cosmic rays which can be measured at the surface of the Earth, enters a scintillating material. And as a muon passes through the scintillator, you get photons of light which are given off in different directions. So the way that our detector works is we have 2 scintillators stacked on top of each other. And when we see light from a muon in the first one and in the second one simultaneously, then we consider that that was a cosmic ray, because there's a lot of background radiation. So you have particles coming in from the sides. You have noise on the sensors. So each sensor itself sees detections, but they're not real detections. They're just the heat in the electronics. So by having two detectors stacked on top of each other, we can filter effectively the common mode, and we can see only the interesting events. The size of the scintillators, so this is much, much smaller than a physics grade detector. It's much smaller even than the Polar Quest detector, but it fits in the box, and that was the main constraint. We read these scintillators out using sensors called silicon photomultipliers. So these are the latest generation of physics sensors. It's the same technology that is used in for scintillator readout in most of the big experiments here at CERN, and it's all electronic and all solid state. So it's very compact, very efficient, and very effective. That will tell us when we see the photons, and we're talking about very few photons, maybe 2, 3, 10 photons. So a minuscule number in terms of the amount that you see in visible light is enough to make a detection. We then read that out with a custom circuit board, which you can see on the right, which has a suite of other sensors. So we're not just measuring cosmic rays, we're measuring atmospheric pressure, we're measuring temperature, we're measuring the orientation of the device. So we know whether it is this way up or this way up, or upside down. We also measure the vibration. So there is an accelerometer that will tell us if we've gone over a big bump, which is very important if you're in a vehicle that's moving. The reason is that shock and vibration can actually also cause false detections. A way to think about this is there are electrons hanging on those silicon photomultipliers, and when you shake them physically, and you can actually shake them loose, and so you can trigger a simultaneous event on both slabs, which looks like a cosmic ray. But of course, having accelerometer data means we can actually exclude that event and say that wasn't a real detection. We also have GPS, which we use for position location and timing. So through using GPS, we can actually time an event that we detect down to about 65 nanoseconds, which is a very high level of precision. And it enables us to do things like triangulate between two detectors. All of this plugs into a Raspberry Pi. So we use the smallest, cheapest Raspberry Pi that sits on top. And of course, for the expedition, we exceptionally put it in a light waterproof case, which has proved very useful. If you move on to the next slide, please. So these detectors were built by me and a colleague, and in the past we've also had students who've collaborated with us to assemble them here at CERN, mostly in our lunchtimes and after work. And on the right, you can see them installed in the back of one of the vehicles. So there were two detectors that made the trip to the North Pole, one called Erebus and one called Nansen. And they're plugged in over a USB with the GPS stuck on either the window, or I don't know if you put them outside of the vehicles, if you manage to get them through the window cracks. It's enough that they can see the sky. So that's physically what it looked like all the way to the North Pole and back again, making the measurements. So that's where they were seated in the vehicles. And Andrew did a lot of work to keep them running because obviously it's a complex piece of machinery, and every so often it does break down. If we move on to the next slide. So this is, sorry, you've got both of the pop-ups already up there. That's fine. So on the right, you can see the world map, and it looks like we're actually not at the North Pole. So this was something we discovered as they went further north on our monitoring software. We use a Mercator projection, which doesn't actually show the North Pole. So if you look in the data rather than the representation, you see that they did actually go to the North Pole. And then on the left-hand side, you can see the readout from the two detectors, which we actually got in real time via a Starlink uplink to a satellite. And you can see that it has lots of gaps in it. So this is what we could read literally the day that they were on the pole. This was the data we got during that day. But the reason that there are big holes in it is because the Starlink and the Wi-Fi was not 100% reliable. Each device has within it a little SD card that logs all the data. So we're now in the process of getting hold of that data, and the next stage for us will be to do an analysis, and we've got some students who are going to help us with that.
Can I just jump in for 1 second,
sure.
actually, James?
Yeah.
This is my wallet. And in my wallet is the folded over piece of tape that has the 2 SD cards that I'm about to hand off to Paolo Catapano so that I can get the albatross off around my neck of the continuous data that these devices collected across the North Pole. I extracted those, and more than my luggage, more than my own clothes, more than anything, I was concerned with the location of those SD cards leaving the Arctic when we came down. So they're now in your hands, Paula. James is correct.
Angela wants them to.
Yeah,
give her a copy.
James is correct. We were thanks to the Starlink able to have fairly continuous uplink, and we have that data. But the problem is actually not the Starlink itself, but the connection between the devices and the Starlink sometimes. However, my sense of relief is tremendous. I'm glad that they're handed over. Okay.
Great. And so that's all for me. If we go to the last slide. There we go.
That's all for you. Okay. Thank you, James. Don't go away. There's one question. There are Italian students following also from Uganda, from Lebanon, and one of the students is asking, it's Luca Loiacono from Istituto Tecnico Ciampini Boccardo. So what's the most difficult technical challenge of building Cosmic Pi to go to the North Pole? You mentioned the Starlink problem that gave you holes in the data taking, but what was the most difficult challenge for you?
I think it's impossible to pick just one challenge. There are so many in building a device that can go and work in the North Pole in the polar environment. So we started with the requirements. It needs to be very small. It needs to be very lightweight because these vehicles, they're very large. They only weigh the size of a family car. The equipment that goes in them is weighed down to the kilo. So as small and light as possible, and it needs to be as robust as we can make it, because it's going to see a lot of vibration during its journey. So there are a lot of trade-offs to be made. And when we look at the particle detectors that we have in physics experiments, they are very large and very heavy and very fragile. So it's the complete transformation of this using the same fundamental technology, but scaling it down so that it can fit in the expedition envelope. And part of that trade-off also means that the detail and the resolution that we have in our sensor is lower than what the Polar Quest had, because it's a smaller detector. But this is the first measurement that we know of at the North Pole on the ground. And of course, this will not be the last measurement on the North Pole at the ground. And I'm sure that the next one will have higher resolution and better. This is how science works.
Thank you very much, James. Thanks a lot. So this closes our session on cosmic radiation. We are now going to change session, and we are talking about something closer to space. So I'd like to call Paolo Nespoli on stage to be the chair of this session. And you can stay, Marco. We have enough chairs. Please come on stage. I don't know. Do you want a break? Are we having a break? We are late. Lunch in Rome is quite late. That's why. Yes. So I'll let you introduce the speakers and maybe give a small introduction about the importance of satellite for guiding this expedition.
Yes. Good morning, everybody. This is the second section here. We heard about Andrew talking about details about the expedition, how difficult it was as a crew to work together overcoming all the obstacles and problems that you had with the equipment, with the cars, with food, shaving this block of fish, this kind of thing. So what we're going to talk about now is more the scientific part, in particular, the fact that we did study the polar region, and we used satellites to allow us to achieve the goals that were the goals of the mission. And of course, the measurements that we have done they are very crucial to expand our knowledge of what happened on the polar regions. And so we are grateful that we had the support of we were able to use space technology to get more information, more data, both for the safety of the crew, but also for achieving things that were never done before, like measurements, like other things. So I will start with the calling Alessandro Coletta. Alessandro Coletta,
Go to
and
volume and then
Axel O'Donnell
Axel can sit there.
to come here and talk about the title is the first satellite photo astrophysicist, but mainly a physicist, astrophysicist. He's the mission director of Cosmos SkyMed, a constellation from handled by the Italian Space Agency. He's responsible for several projects in his career. He is a professor at University Gabriele D'Annunzio in Pescara. He writes, he speaks, has a lot of everything, does a lot of things, and very influential. And also there's Axel O'Donnell. Axel O'Donnell is an engineer, an environmental engineer, right?
Yes, correct.
And he's through EGEOS is responsible for managing acquisition, interpreting, but also distributing the images from the Cosmos SkyMed constellation. So, Alessandro, it's all yours.
Thank you, Paolo. Good morning, everybody. So a few words just on the Cosmos SkyMed. What is Cosmos SkyMed? Cosmos SkyMed is the largest investment in Earth observation by Italy. So it is a X-band radar, synthetic aperture radar constellations. It means that the sensors on board don't use, but we don't see the Cosmos SkyMed. The next one. So we have on board, okay, again, so you click, no. So go. Yes, animation. Okay, no, doesn't matter. That's not important. So you go back to the second slide, this one. Okay, the first one, the second one is the same. So anyway, we use the X-band radar sensor. So they use microwaves and not visible data, visible light like our eyes. So this is very important because we don't need the sunlight, and also we can pass it through the clouds just to observe the targets. And what the next band sensor, radar sensor, makes is just to collect the backscattering echo signal received by the ground, just to make everything, just to understand everything, more or less. So now we have 2 generational satellites. So, okay, so the first generation is now made of 3 satellites out of 4, because also satellites dies. So we deorbited one satellite a couple of years ago. Now we have 2 satellites of the new generation, and we launch 2 other satellites, the first one the next year, and the second one by the end of 2026. So we will have probably 7 satellites working at the same time. What is important is just to underline that these satellites have been designed just to last 5 years, more or less 5-6 years. The first one was launched 17 years ago, and it's still operating. So we have satellites that are operating 3 times with respect to nominal life. So we are very proud of this, like nation. So it's very technologically advanced, important constellation. So this was Cosmos Sky. We were not involved in the Transglobal Car expedition until the end of March, when Fabrizio Bernardini called me and asked me, can we do something, because we are now in a complicated moment. So there are no satellites data just to help us reach the North Pole, because the other constellation were not able just to go above the 85, 86 north latitude. So we say, why not? Why we can try it? But it was something difficult, because you know that every mission has a data policy rules, some specific data rules. In this case was something in the middle, the institutional and the commercial one. So we didn't know what to do. But at the end, we just to have a decision taken individually by me, like mission director, and I asked Axel, like what is the commercial provider of ASI, EGEOS, why don't we try to help them? So we start just to acquire images every day. So 200 kilometers by 200 kilometers, and I don't remember which was the resolution. 50 meters resolution. So we had a lot of fun just in supporting the. And at the end, at the very beginning of April, we asked ourselves, why we don't took the first ever taken images of the car parked close to the polo. So we tried with the higher level of resolution, of course, because 50 meters is too much. We just give them some simple rules. Don't put all the cars on the same line. So it's just a better random wave to have the maximize the backscattering of Cosmos. And now Axel will show you the image. Just another words to the crews. You will go to the South Pole. Do you want the first ever taken image of the South Pole? Thank you. I leave the floor to Axel.
Okay, so the next slide. We are already, Alessandro said about the Cosmos SkyMed mission, and it was important to say is that the satellites are able to acquire at every moment, and because they are on a sun-synchronous orbit, we have several acquisition opportunities at the North Pole, because at the higher latitudes, there are multiple orbits which are able to see. So we have a lot of imaging capacity at higher latitudes. And the sensors are able to acquire data with different resolutions, some from very large data with low resolution to smaller data with very high resolution. And this flexibility is, of course, important for the different kind of applications. Next slide, please. So as we said, why there was the need of using Cosmos? Because thanks to its orbit and especially to its viewing capability to the side, they go to 60 degrees of their capability. As you can see from this picture, which is the visible range of a satellite on a 24-hour days, with Cosmos SkyMed, we are able to cover the North Pole. Other missions have this little hole in the middle, so they are not able to go up to the very last point. And so there was the need of asking the support of our Italian mission. And so here, the first acquisition that we made, it was on 30 of March. It was a Scansar 2 scene, so it's a 200 by 200 kilometers with about 50-meter resolution, a pixel size of 10 meters. The concept, the operational concept that we had is that to acquire in advance where the team had to go, so that while they were sleeping, we tried to acquire the data and make them available. So when they start in the morning, they have an overview of what they should expect in front of them to go on. And here at the end, we continue to follow up to the North Pole and then down to Greenland. So we're more than 60 scenes provided from the 30th of March to the 6th of May, and until they reach again a firm ground. And so how does it look as our image over ice? That's an example. So as you can see, it's a kind of difficult to understand. It's not easy to understand the backscattering. Typically, where there is a dark area, it's water, especially it's very dark. But it could be a mixture of water and floating ice, or other things. So it's something for experts, or at least it's something for people that been there. They have a day-by-day knowledge. They see, okay, this is this, and they start to grow up their understanding of the pictures and to move around. One important thing to notice is that this image, for instance, was acquired at 3:22 UTC time. If you go to the next slide, it's done by the same satellites, the orbit after. So each satellite takes about 90 minutes, 1.5 hours to make the complete world and come again to the same target. And you can go back again and you go forward. So you see that there is a little movement. Why this movement? Is because, as we have been told before, ice is moving, and is moving very fast at those latitudes. And so if you go to the next slides, we can calculate in this example here that it was only 90 minutes, but the shift was already a few meters, and in 1 hour, 400 meters in that place. But there were other places where it was much faster, the movement.
The tricky bit there, just to sort of jump in,
Absolutely.
is that we have a GPS locator where we are, on the planet, but the image is moving underneath us, basically. And so there would be times where we were like, wait, we think that this line is over there, just that we know the ice is moving that way. So we're able to actually juxtapose and put a correction on the corners of the map to move it underneath us.
Exactly.
But it took a lot of working together, a lot of back and forth, a lot of thinking, and showed those technical options on every day. Hardly. Oh, sorry. It was extremely complicated, and thank you for your patience with us, because we would go to sleep at night and sometimes move kilometers during the night. And so it was important when we got the image to make sure it was as close as possible to where we really were. And then even as this is a very good illustration of what you've just done, in 90 minutes, it could move quite a lot, and it messes up where you think you are.
Absolutely. Considering also that, of course, when the idea is to take a large picture because we don't know exactly where they are and where they will go following the best route. And so we have to take a larger picture and hope that they find the best solution to move through. Next slide. So and then the question is, why don't we take also, as Alessandro said, a picture of the team when they are arriving at the North Pole? The problem is that we didn't know when they were going to arrive at the North Pole. And by the way, at the end, they arrived on Saturday in the evening. So we are not generally not working on Saturday and Sunday to follow it. So what was the concept here? It was that we started on Friday, we placed as many acquisitions as possible. And they said, okay, we will be able at least with one of them to take them. So if you see in this list here, we had these are the high resolution images. So which are a small path located on the North Pole. And so from Saturday to Sunday, we made several acquisitions, hoping to get them. Then we started to look at the images, but again, it's not easy to find them, to recognize the car, because it's a mess with all those eyes. And so we asked for the GPS position of the team, and they provided us the track of the GPS position. And so we saw that the acquisition on Sunday morning at 2 a.m. UTC was the closest to the polar because they arrived at in 8 in the evening. And so we were able to localize more clearly. And if you see here, this GPS track, you see up there, that's the North Pole, because the team arrived and then they made a few circles, they made the pictures, and they had a moment of fun at the North Pole. And then they went a bit down to find a safer place to spend the night and stay for the next hours. So if you using the GPS, knowing that the satellite acquisition was at 2:54 UTC, in the next slides we see the position of the GPS. It was at 2:10, so 1 minute away. And if we zoom here, you start to see. But if we zoom to the next slide, here we have the details of the 4 cars. Of course, it's not a nice picture, it's a radar image. So you have again to think that even if this picture has 60 centimeter resolution, so it's what is defined as a very high resolution picture, still the objects, you have to think it's a signal coming from 600 kilometers, a radar signal reflected by the cars and going back. Absolutely, yeah.
Yes, just what you, sorry. And this is for people that do not know the radar image. For the visible light, for our eyes, everything is white. here, okay? So this can show how the radar can see more than our eyes, of course.
It's very...
The four bacteria are the...
Not like the four bacteria, yes, exactly. The satellite...
620...
Something like
No,
kilometers.
kilometers. Who said meters?
No,
Yes,
the satellite at 600.
They are the low orbit, the low Earth orbit, that's something between 800 and 600, 800.
No.
620 kilometers.
600 kilometers.
And synchronous orbit. So
see the
yes,
view.
of course. Hey, of course, because it's become technical. Because the radar cannot see on nadir. It must be in a squinted way because of some geometrical distortion. So we are obliged just to use the squinted mode to apply.
So you're not vertical.
It's not a vertical. It's on the side looking. Yes. So in the next slides, you see, of course, 1, 2, 3, 4. So we had the 4 cars. And the funny thing is that when I found this image, I think I found them. To be honest, I did not know how many cars there were. And I said, I count 4 cars. And they told me, yes, they are 4. So I said, okay, I got them perfectly. And just for your consideration, this is it's a satellite acquisition from the 2nd generation of Cosmos Skymet. So the new satellites which allow to have double polarization. So to give you an example, this image that you see here is what we call an HH polarization. It means that the signal was sent with the horizontal polarization, and the signal returning was also measured in horizontal position. But at the same time, if you go to the next slides, we have also what is called an HV. It's next one.
Only HH.
HH. No. This one, HV. So it means that the same signal, horizontal signal, here we calculate the return signal in a vertical position, so 90 degrees difference. It's darker, you see there is less reflection with this polarization. But if we go to the next slides, by putting together the two polarization, we can also generate a false color image. So in this bluish, we gave them this bluish effect. And so this was at the end the picture that we also posted on the social media, saying, okay, we have the first picture of cars parked in the North Pole. Okay, next slide. Thank you.
Can you go back? Can you go back a second to the picture there again? Because what is this? I'm curious. What is this? I mean, these are the cars, but this
looks like a crater. Yeah, it was a large.
So you marched a lot on the ice.
No, it was actually
you were dancing or something.
Well, we were, of course, dancing. No, it was an area of ice that was basically a pressure ridge that had pushed up in that pattern. It cracked, and it was a bit rough. It just happened that when we arrived there, the point of 90 degrees north was on one of those rises, so we used that as our location at 90 degrees north there. But the ice was pushed up in front of us. It happened perfect. The timing was perfect.
Okay, I think thank you.
There is a question.
Yeah, thank you very much for the thank Alessandro and Axel. And Paola is collecting questions. So here we are with some questions. Go ahead.
But I also think they can stay with us because nobody else is coming on stage. Yeah, maybe later. Okay. Anyway, so there's a question for Alessandro, but of course it's for both of you.
Yes.
You already explained how you obtained the first photo, so this shouldn't be repeated. But the second part of the question from Gabriele Poggio, another student from the same institute, Ciampini Boccardo, is what are the practical applications of this photo, if any?
No practical application. It's just a media effect. But what we want just to have publicity for Cosmos Skymet, just to show what Cosmos Skymet was able to do, is able to do with respect to other constellations. So the specific goal was just to media to have to have some bigger media effect. So, but you don't have practical images of this one, more or less.
In this one specific, not, but consider that the use of radar imagery for like Cosmos Skymet for star sea ice, it's one of the most important applications for radar data. there is, for instance, a huge program from the Copernicus, European Commission Copernicus project, which is called SAR-Sea Ice, and it's done in order to monitor the concentration of ice at sea to support navigation of ships. And this is something that is achieved by using radar images like the ones that we provided to the team. Of course, the team was full ice, but you have to imagine where there is floating ice and space to move with the ships. And this is a really important applications. And having a team validating on the field and doing the classification, let's say, of the different kind of ice. We have made a similar project a couple of years ago with the Italian Navy, where they made what is called the High North campaign in North of Svalbard. They made a similar approach to do a classification of ice, and this is the first step to develop automatic artificial intelligence, automatic classification based on satellite images, and provide immediately the picture to the ships which are navigating.
Yeah, and just to not to extend that, but just to jump in for practical application, we were the practical application. We would have barely been able to do it without. And you know, we've done it by standing on ladders before, but drones, but not nearly as good as we were able, and as well as we were able to do it with these images. And so there's probably not going to be a lot of people driving the same way that we went over, maybe never again. But for anybody navigating, for people monitoring migration patterns of animals, for any seafaring people, like, obviously it's crucial. And so thank you so much to you for what you were able to achieve for us. And I hope that the experience can lead on to more excellence. I really appreciate it.
Thank you. Thank you, Alessandro. Thank you, Axel. Thank you for this. I would like to acknowledge Francesco Bernardini, that is the one that came up, Fabrizio Bernardini came up with the idea of using Cosmos SkyMed for this, because nobody had the idea before, but he said with his knowledge, his contacts, his capabilities to actually put together the things that we have to help everybody. So thank you, Fabrizio. Thank you for everything. Thank you for coming up with this idea and saving their day sometimes, right? Or helping a lot. Okay, very good. So I will call up the next speaker, who's a friend, and I am a former member of the European Space Agency. Tommaso Parrinello is still a member of the European Space Agency. He is also a physicist, right, with a PhD in remote sensing, so exactly on what we need to do now. And he is the ESA mission manager of Aeolus and Cryosat. So go ahead, Tommaso.
Thank you, Paolo. Good morning, or good afternoon, actually, to everyone. For me, it's a pleasure to be here for two reasons. As Paolo said, I am a physicist, and Fermi and his group has been always, for us, very inspirational. And the second thing is we were very happy to support this fantastic and crazy thing as well. When Fabrizio came, he said, "Can we support?" I said, "Since I have been there, do they know what they're going to face?" I said, "Apparently, yes." Okay, so let's go then. Let's go with the slides. I will try to very quickly. Okay, this is not my slide. This is, there you go. Let's try very quickly to go through what can we measure with satellites, in particular, what we have been measuring with Cryosat. Cryosat is, I will go very quickly through the presentation. It's a satellite which was launched some years ago. And what we're going to do here is we're going to give you some information. In 10 minutes, it's very difficult to tell you what we have achieved, but I will go through the main ones. But before we do that, I would like to have two slides of introduction about why are we doing this. And because when we speak about climate change, usually, everything should be an animation. Okay, fine, doesn't matter. When we talk about climate change, we usually refer to the fact that our planet the temperature of our planet is increasing, and increasing a lot. And if we usually refer to this to the beginning of the 19th century, and what we see in a graph like this, can you put the slide, please? We see that there is an increasing trend, which when we get the slide, okay, stay with me, yeah? Okay. You see that from the 1960s to now, you see this red line, which is the average of the time, the average of the temperature during the months. You see without any doubt, there's an increasing trend. Now, I can say today that this is because the carbon dioxide is increasing the temperature, but you know this. And there's another important thing which you can observe here, and it's just at the end, which means that in the last 15 years, we have measured basically at least 12 records. So not only the ice is melting, but also the temperature is increasing. And as you can understand, there's a direct consequence about this. What does it mean that the planet is increasing its temperature? It's accumulating energy. Energy, it's the most important thing in the universe and also on Earth. Next slide, please. I'm sorry, there was an animation. So what we are seeing is that this energy is being accumulated by our planet. And the element which accumulates most of the energy is the water, is our oceans. And just to give you a small detail, and then we go to the satellites. For example, in 2019, which was one of our records years, the oceans just increased by 0.075 degree, which is very little. But this, if we compare to what the energy is, in terms of little, in terms of how much increase in temperature, but corresponded to 228 10 to 21 after Joule, which means is basically only in that year, we absorbed the planet, the equivalent of 3.5 billion energy released by a bomb like the one in Hiroshima. The same thing happened in 2023. Actually, if you look at the graph on the right, the temperature was higher, so it could be like 7. And 2024, we still don't know, but apparently it's going to be another great record of since we are recording. So every year we are accumulating billions of energy equivalent to the nuclear bombs. You can understand that it is insane energy and something is happening to our planet. And what we are trying to do, next slide, please. What we're trying to do all together around the world, the scientists, the people who go and do what this expedition does, but especially satellites, because from satellites we can measure continuously what is happening in the different poles. We are trying all to put a lot of satellites together. This is all the satellites we have launched in the European Space Agency, and 80% of those satellites are directly or indirectly measuring the effect of climate change. The one you see here just on the top is CRISAT. So CRISAT was launched next please, was launched in 2010, has been there now for more than 15 years. And it had two important, I'm not going into the details, it has a radar, a Doppler radar, altimeter actually. And what the objective was to be achieved, this is important in 5 years, is one is to measure the ice thickness and how this is changing in the poles. Why actually in the Arctic? Why in the Arctic? I think it was mentioned before. If we get an increase of 1 degree around the planet, we get 2.5 degree in the Arctic, because what we have is called the Arctic amplification. So the second point, objective, very important, was how much Greenland and Antarctica are melting and what are their contributions to the sea level rise. So we have discovered many things. We have basically, unfortunately, there was a nice animation there, but I just want to say that we have been confirming how the thickness, because as Andrew said before, it's very difficult to measure. But we have done it because we have a very special altimeter on board, and how this has been changing. But not only, we, for example, have found with the sea ice that the ice, which Andrew was mentioning before, which is fast to the Greenland, fast to the land, is changing a lot. And we have discovered that actually it's declining almost 60 to 100%. So we know that at the North Pole, the ice could be a couple of meters. Close to Greenland, it could be 3 meters. This is why sometimes it's difficult, as Andrew says, going through, because you just float and you change from one and you just can sink. But what we see is that uniformly, the ice is thinning. And we also did something very interesting. There was an animation, I apologize, is that we are now able to provide a year-round satellite sea ice thickness. Why is this important? Because we have been now accumulating data for 15 years, which is the longest, the satellite is the longest climate data record on history, done by one instrument. And this is important for climate, it's important for the scientists, and it's important to understand what's going on. It's important for the models. Okay, and thanks to this, we are now able to measure sea ice thickness in the Arctic. Next one. So we said, but where we see most of the problems is in Greenland and also a little bit in Antarctica. And after 3 years, as I said, we're going to present results after 3.5 years. We did it. And what we find out was quite astonishing to us. We find out that Greenland, which is on the right side, and the red part is basically places where the ice is thinning 10 meters per year, not per century, not per every 20 years per year. This was a result in 2014, just 4 years after 16, I think, yes. And what we measure, it was like we were losing 270 gigaton of ice. I will come at the end to explain what this means in practice. Basically, it's 270 kilometers cube of ice is melted every year. It was really surprising for us. At the same time, we did the same thing in Antarctica. And since then, Antarctica, with the satellites we had before, it was not clear whether we're losing or gaining, but especially on the left part where you see red, also we found there that it was losing 160 gigaton or kilometer cubes of ice a year. Now, in the last 15 years, we have used different collaborations with different satellites along all the space ages in the world, and there was an important paper collaboration which tried to reconcile all these different measurements. And what we came out, this is an update really recently, is that basically every year now, on average, since 1992, we have been losing something like, contributing to something like 21 millimeters. But this is taken an average since 1992. If we look at the recent years, the last 10, we are losing like 300 gigatons per year. I will explain at the end what the gigaton is to give you an idea. Next one. I think I know that Christian was going to be here, so I probably leave this to him. Just very quickly, also recent results, very complicated to measure this. We also see that the ice shelves in Antarctica are as well a negative balance. Next one, and we're almost at the end. Now, we always think about Antarctica, Arctic, but we have glaciers all over the world, and this is what we call the third pole. What about them? Well, before CRISAT, no other mission could have measured with high resolution what was going on over there. And thanks to what we have an interferometer on board. Thanks to this and to a technique which we have discovered doing it, it's called SWOT, we were able to map the complete, almost the complete, I will say, a situation of the glaciers around the world. And surprise, surprise, they are contributing to 272. So if we put all these things together, I know only for the glaciers, and then we go for the conclusion, only for the glacier, you can imagine that since the last 10 years, we have completely lost a cube of about 14 kilometers per side since then. And if we combine the glaciers and we combine the Antarctic and we combine the Greenland, what we get something like 600 gigatons. 600 gigatons means more or less, you can imagine the entire size of our country, Italy, with a layer of ice of 2 meters. This is happening on average every year. Next slide. I'm sorry for the animations. What happens when ice from land goes into sea? We know what happens, the ocean rise. And what we are measuring now, and then this here, as you can see, we're measuring for the last 40 years with the contribution of all the satellites. So this is not a result of 2 scientists. It's not a result of an agency. It's a result of thousands of people who have been working for 40 years doing this kind of measurement. And what we see that on average, we are losing like 3.6. This is the result from February, but I have been saying this thing for the last 15 years, and when I started, it was 3.1. Now, 15 years later, it's 3.6. And you probably, if you have a scientific eye, you can see that probably at the end we're accelerating, and it's not 3.6, but it's 4.4. Next slide, and I go to my conclusion. So is it only sea ice, and does it bother us? Well, if you think that in 2100, no, at the end of this century, we're going to be like 10 billion people. And if you think that 10% of the people are living close to the coast and not more than 100 meters in altitude, well, the problem is going to be not only scientific, it's going to be, I will say, political, it's going to be economical. And we are now living into, when I was saying this thing 15 years ago, it was like a scientific thing, yeah? Okay, you scientists, you always exaggerate and so on. No, now it's something, we are living in it. Now, finally, there are now two words which you can hear in the newspaper. One is climate change, and the other one is artificial intelligence. And these are from the IPCC, which is not only increasing the ocean, but it's also increased. There are only 8 incredible impact which we'll see. And if you just go through them and I leave it for your eyes, you can see that it's not only the sea level rise, but it's much more than that. So climate change is really probably the most complex challenge of humanity. And as the speaker before, not only for scientists, but also for the governments which are coming ahead of us. And as I think a speaker said before, definitely what we can do, we cannot change it. I mean, forget about changing it. We only can adapt. And I think we have done also this in the past. Thank you.
Tommaso, stay a little bit. Thank you for this presentation. I am a little bit scared, actually. But I understand that you guys collect data and you present the data, and it's on us to understand what's going on and figure out what we need to do to at least stabilize the situation and maybe making it better. But Paola has a question, right?
Yes, this is a question from Davide from l'Istituto Tecnico Ciampini Boccaro Novi Ligure, the project Spazio alla Conoscenza. He asks, what's the impact of global warming? I think he means what's the anthropic impact on the thinning of the ice thickness?
Well, what I've been showing in the presentation, basically, we are seeing everywhere now, not only in the Arctic, but also in the Antarctic, is thinning, and we are not losing only fast, but we are, we're not losing only ice, but we are losing it fast. And there are now different sensors, different satellites, we're all measuring the same thing. And what is, as I said, what is the result of this is that the world is changing. And another thing which I would like to say to the guys is that sometimes we think that this is happening in the South Pole, and it's fun for the people who go there and drive and trying to make interesting results, or to the Arctic. Everything which is happening in the Arctic is about us, because a change over there, it means a change in the whole climate because of our planet.
Okay, thank you, Tommaso. Thank you very much for the presentation. I got scared. I think need to think about something to do something, right, Fabrizio? We need to come up with something. So we on the schedule here, we have a presentation by Christian Haas from the University of Bremen. It was supposed to be a Zoom connection. We are having a little bit of problems, so we decided to
skip it.
Gain the time, right? But
yeah.
There is a question
there is
for
a question
Christian.
For Christian, which he answered remotely.
He did answer remotely.
So
okay.
I will ask the question on behalf of the student, and Andrew can read the answer.
I will play the role of Christian Haas.
Yes, the student is Marco Baldoceda of Liceo Scientifico Enrico Fermi, Genova, and the didactical project is Astrofermi. So, question for Christian, which new instruments or technologies are being developed to improve the measurement of the ice thickness in polar region?
I will try to answer this with the authority of Christian Haas. He says, ice thickness can be measured by radar and laser altimetry, and there are new ESA and NASA satellites dedicated to that. ESA operates the radar altimeter on Cryosat, and NASA operates the laser altimeter on IceSat. These satellites measure the ice of the height of the ice surface above water, called freeboard. Because ice floats, freeboard is correlated with ice thickness on the iceberg principle. We can go into that. However, accurate ice thickness observations require good knowledge of the thickness and density of the snow on top of the ice. That knowledge is limited, and therefore ice thickness estimates have a high uncertainty of more than 5.5 meters. Our expedition, the TRANSGLOBAL CAR expedition, used electromagnetic induction sounding, that's the device that we pulled behind the vehicles, to measure the thickness of the sea ice, because radar does not work due to the salinity of the ice. EM sounding, electromagnetic induction, was developed by us, by the Alfred Wegener Institute and the Christian, and provides accurate ice thickness observations of 10 centimeters of accuracy with very high spatial resolution, so that the important small-scale variability can be observed. For example, the thickness and distribution of the thick pressure ridges and thin new ice. I actually went over that with Christian about how he's able to filter out the results where we're going over pressure ridges and so on. I think the answer is that yes, that a combination of the radar and laser altimetry cryosat, specifically that we just heard of from Tommaso, and then some on-the-ground truthing observation with the electromagnetic induction in order to triangulate that data is really the best way to get everything together and go forward. But certainly we saw empirically the same thing that you see from the satellites. It's getting thinner and fast.
So thank you to Christian and to Andrew for playing Christian and answering the question. And
so now it's up to you. So you're moderating, but you're also speaking. So
I see that the next session we are about an hour late, by the way. So we'll try.
No, we was foreseen to finish around 1 o'clock.
Yeah, but start at 12:30.
Yeah,
they start an hour late. So this next part of the section here is talking about what's next, the Transglobal Expedition towards the South Pole. And so I will ask Andrew to take the first part of the question and or this part and talk about this one.
Yeah, great. And I'll do this quickly. When we go to Antarctica and cross Antarctica, we will be measuring a number of different snow and ice factors down there also. But what this connects well with what Tommaso finished with is that the effects of that we're observing are not only on the poles, but in fact on any glacier or any body across the Earth. So we're next going after Europe, we're going to Africa and then sub-Saharan Africa, and our hope is to go to a mountain there, Mount Stanley, known as Mount Nyalima locally, and do some measurements with partners. We haven't really announced this yet, but we're hoping to actually do some glacier analysis, both for extent and thickness there. There is a glacier, there's snow in Africa in several places, and on this mountain, close to the equator. Yeah, not right on the equator, but close, which it surprises people, but at altitude, of course, is about 5,000 meters. And they have seen not only a change in the thickness of that glacier, but a quick movement of it and a more dynamic movement of it in recent years that has had a huge effect. So I'll just briefly to anticipate what we're doing next. We're concerned not only with the poles, but with the story of loss of ice thickness and density around the world. So we're hoping to lean into that, and perhaps we could talk more about that. So then I'll hand it back to you, Paolo, so you can go on with the next things. But it's a serious problem. We're taking it seriously, and we're hoping to log more data.
Thank you, Andrew. Thank you for this. And I think we got some questions via Zoom, right? So we put them up on the screen. It works like that. Okay. Master Badru, does the expedition and the study on the cosmos ray gives us another explanation how the universe was formed from? Was formed from the Big Bang theory? Who can answer this?
Marco. This is for Marco.
Marco.
Oh, well, actually, studying cosmic rays is looking at the universe. So we are looking at what happens in the universe, what happened many years ago, because cosmic ray arriving to us started their journey millions of years ago. So it's looking back, and studying cosmic rays is fundamental physics, and it's something that can help us in understanding the universe at all. That's it. Anyway, it's a huge question.
Can I speak to that point just for a quick second? I'm not the scientist of cosmic ray here, but so I was lucky to learn, thanks to the support of Paolo and the people at CERN and so on, and in your team, some of the at least correlative effect or correlative observations of cosmic rays. We went to the cloud chamber at CERN, and with the knowledge that free particles or these rays can have an effect on the particle effect on cloud formation, and that in turn can have an effect on climate, is massive. And then I learned also independently or through the source that there is a correlative effect with a couple of weeks lead time on seismic activity in the Earth, right? With cosmic ray flow change. Is that correct? Yeah. So it's not a causal relationship. It might not tell us where an earthquake would happen, but it actually seems to predict with some level, I think, of 2 degrees of confidence accuracy that there will be more seismic activity. So something's going on, and in order to understand the relationship, we have to collect more data, right? That's our project.
Very good. And I think the second part here is to do with me talking about light pollution, which and by the way, it's light pollution from space. So it's not light that's coming from space, it's the light from the sun that comes from space. It's exactly seen from space. So, and we had an example yesterday evening. We had this beautiful dinner in central Rome, and Rosie and I were trying to look at the stars. We managed to pick up something, couldn't really figure out there's an aircraft, there's a star, it's a planet. Then Rosie came out that is, what was it? So this gives us the fact that, you know, we, in the old times, when I talk the old times, I talk 1,000 years ago, people at night could see this marvelous sky on top of them. I've had the chance myself to see it couple of times when I was out at sea in a little island, and I could look at the sky, and I never saw the sky in that way, and it was incredible. And I can only imagine what, you know, 1,000 years ago, the people every night would have the capability of seeing these things, how beautiful it was. But this is not only beautiful, it serves us for allowing us to understand ourselves and understand where we are and where we are going. So I was planning to show a movie. No, but I don't think will make sense to show it, but it is a movie taken from space where we actually see the lights all over the world, which is very interesting because it shows that we as human beings are everywhere in the planet. So it's kind of amazing because from space, you actually see that we are everywhere. You know, you don't see it during the day, but at night, everything lights up. It's like a Christmas tree with lights everywhere, and every single point of lights that you see, it means that there are thousands, if not millions of people in that place. And so we eject so much energy in the atmosphere, which contributes to enhancing or increasing our temperature of the planet, but also blocking us from being able to see the sky. And so this is something that we need to think about. We need to probably have better way of putting light on Earth when we need it at night. I think I talked to many people about this problem because I was in my little town northern of Milan, and at night, at 3 o'clock at night, and I could have read the newspaper sitting in the main square because there was so much light. And so I talked to the mayor and I said, why are we using so much light? You know, so that we can look around, but it's so bright that we can read the newspaper at 3 o'clock at night. Who gets in the middle of the square at 3 o'clock at night to read the newspaper? And he said, well, we tried to lower the intensity, and the citizen complained because, at least that's what he said, we do associate lights with safety, and therefore taking out the light from the street or from the squares or from the cities has a little bit of impact from a psychological, our psychological point of view. We need to understand this and being able probably to take it and lower a little bit temperature. I was living in Houston for several years, and it was funny because there was one light not far away from the house, then nothing for 100 meters, then another light, and we were in a fairly densely populated area, and there was no need to have lights everywhere so that all the street are lit. Tommaso, No, se vuoi dire qualcosa, vieni. Come up and do and say it.
The answer of the mayor, I mean, is the same answer they're giving, which is totally wrong. There are I would say regulations, very tough regulation, especially for example in Lazio. And I know this because I am a bit of a astrographer as well, and I'm fighting with all my neighbors because it's not about reducing the light, it's about using the right light, and that is the problem. And they say security, it's an excuse. It's just so to say there are regulations, and also Europe now is trying to put these regulations in place, and it's a lost battle. I fully understand, Paolo.
No, it's clear that we need to do something. It's clear that with lights we feel more safe. It's clear that the easy way is to put there a huge amount of lights. Some of this light will actually get to the ground. We need to start working on thinking about this, producing light, but sending the light in the right place. That's sending light in space or send it outside is not the right answer. We do yes. This today, and we probably need to pay attention and be a little bit more attentive to this.
Absolutely. Just to say, Matera has worked with Unioni Astrofili Italiani, and
no, but I see that around we start putting different lights. It's true that from space, by the way, Italy is one of the most
Christmas tree.
Is like the most Christmas tree in the world. But and then you pass over the Alps or even over Switzerland, it's not so lit up. So we posted them, the European Space Agency, NASA, the Italian Space Agency, all the space agency take our footage that we take from space and build these videos. There are several online. And by looking at them, again, we can see how beautiful the planet is from space, but also how we are probably overusing the resources and not paying attention on what it does to the planet, and not so much to the planet, to our capabilities to stay on the planet. That's the problem. It's not that we are going to this. I always think that people ask me, oh, how fragile a Earth from space? And I said, Earth doesn't care what we are doing to the planet. It's more that we are going to change the parameters that allow us to stay on this planet. We'll probably disappear. Earth is not going to go anywhere. It will be there. But, we do care about us, so we need to pay attention because of this.
I just wanted to say that you both, Paolo and Tommaso, replied a question that was there for you. The answer is already contained in what you say, but just I wanted to credit the student, Erika Nikusokan-Tayar from Liceo Scientifico Primo Levi Borgo Fornari di Busalla. She asked exactly this question: what are the main threats of light pollution, and what are the measures to adapt? So I think in your interventions, you already answered to the questions.
All right, very good. So I will ask Rosie Mondardini to come up and give her presentation. And then if there are some more question and answer, we will have them, okay? Go ahead, Rosie.
Okay, thank you, Paolo. Thank you, everybody. Actually, this is like the perfect intro to what I'm gonna talk about. That is that while the crew was doing everything that you heard about, basically, they were also doing something very special and very important, because they were promoting citizen science. And I don't know if you ever heard about this concept. Citizen science are these projects where citizens, meaning you, general public, everybody out there, collaborates with researchers to do research, scientific research. And they collaborate in many different ways. So the crew did it in 2 ways. In one way, they were themselves citizen scientists. None of them has a degree in physics to collect cosmic rays, but they did it. They used the detector, and they knew how to do it. So that is a very concrete way of promoting citizen science. But at the same time, they were also promoting existing citizen science projects. And yeah, if you can show, during the the North Pole leg, they promoted particle hunters, so again about cosmic rays. And basically in this project, you can download an app, and with this app, you transform your phone into a cosmic ray detectors. And then by synchronizing and networking all of the smartphones, you basically create the biggest detector that you can actually build. And this is a competition, and I'm mentioning this is the past somehow, but one of the teams that are actually online, the students from Uganda, they managed in this competition to be 9th in the global position. So very successful and very nice inspiration for the students. Next slide, please. So what is happening now, and this is why all of this talking about light pollution, is that in the European leg of the trip, we are promoting participation in Globe at Night, which is a project that was created by NASA originally, and that is now basically managed by the Association of Universities that study astronomy and study especially light pollution. And why there is the need to monitor light pollution and to basically collect data about light pollution, because we heard a little bit of it, a lot of consequences, bad consequences, both for humans and for animals. Not knowing anymore when it's dark, when it's night, and when it's day is really confusing for the circadian rhythm of our internal clock, basically, but also the lowering on the production of melatonin. So with a lot of consequences from sleep to depression, headache, stress, and many more. So what are you supposed to do if you want to join Globe at Night? That is actually what we tried to do last night. Basically, you go out at night at least 1 hour after sunset, when it's supposedly very dark. You look at the sky, and you have, depending on where you are and the period, you have certain constellation that you want to look at. And then you have a form that you can reach, with your smartphone or with a computer. You look at the sky and you answer the question to the form. Very simple. There are periods of data taking because you don't want the moon to be there. So we just finished one today, actually yesterday. Coming up from the 26th of July to the 4th of August, there is another perfect data taking period. And depending on where we are, in the north of the hemisphere or in the south, you have different reference. But you find everything on the website of TransGlobal and also the website of Globe at Night. So very quickly, what you create, basically, if you can go to next slide, is these are the data, the map that you create. These are the data provided up to now. If you go to next slide, you may have the impression that Europe already has a lot of data, but not, in fact, not. So please, feel free to join also from places like Rome. So next slide, please, is what we will do in Africa concerning citizen science. And we are still discussing the different options. This is a very good option, and I really hope we will go there. This is basically mapping the presence of water sources in Africa. Donate Water is an existing project that has been created by a group of students, actually, and is supported by the Citizen Science African Association. And also, it has been designed together with national statistical offices. And if you know a little bit about the Sustainable Development Goals and how each country is supposed to report to the UN, are the statisticians that will do that. And so if you collect data in the right way, your data can be used to actually report to the UN. And what you create, again, if you go to next slide, this is what is happening right now. They are in Nigeria. So these are the data that have been collected up to now. And one of the ideas could be to actually extend and scale this project up to all of Africa. So we will see. Thank you very much.
Yes. So there's a question for you, Rosie, as well, from Beatrice Salonia, Liceo Scientifico Einaudi, Siracusa. So how can the Citizen Science Europe and Africa project contribute to scientific research What are the most important achievements?
Well, both of them contribute basically in the same way, that is collecting new data. And for all of these studies, for the scientists, it is absolutely necessary to prove with data whatever you are kind of promoting or claiming, let's say, with your theories. And both projects are data collection. So mapping in one case of the quantity of light pollution, and even in the other case, the presence of cosmic rays. And I think that, you know, listening to the presentations before, you know how important both are for the scientific community.
Thank you, Rosie. Thank you. Thank you. Is there any other questions here from the floor, or from Africa or something? Or if not, we will, I think, close this section. I actually heard an interesting thing, is that in Antarctica, you probably will still use the image satellites. So we welcome ourselves again to come back when you go around the south and talk again about what happened down there.
Yeah, obviously it's different provinces, problems. It's crevasses that we'll want to know about. So we'll talk more about what we need. But there are dangers everywhere on the ice.
So, Dr. Bracco, I was going to thank you for having us host here, but you have a question. Go ahead.
Come back after the end of your next activity.
So this is an invitation to come back at the end of the expedition.
Thank you. It would be an honor to return. Thank you very much. Thank you.
All right. Thank you. And so what is next? Food. I say here lunch at Centro Ricerche Enrico Fermi. I would like to thank again Dottoressa Bracco for the hospitality. Thank you again to the Centro Ricerche Enrico Fermi for hosting us today. And thank you for all of us, all of you, for exposing, telling us all this part here.
And thank you, Paolo, for playing the game.